Let's talk about what's going to happen to stars that have different masses. Now, everything we've talked about so far has been about the life cycle of stars like our sun. Our sun, as you recall, is right in the middle of the Hertzsprung-Russell diagram. The most The biggest indicator of what's going to happen to the life cycle of a star is its mass. Mass is the key to determining how it's going to live its life and how long its life is going to be. Stars like our sun that are kind of medium mass, they are expected to live about 10 billion years. Stars that are very, very big, up here in these bright, big blue giant stars, they are going to have a lifespan of about 10 million years. Now that's 1/1000th of the lifespan. That is so much shorter than the lifespan of our sun. Low mass stars, down in this lower right-hand corner of the Hertzsprung-Russell diagram, they are expected to have lifespans of about 200 billion years. That is 20 times longer than the life of our sun. And it all has to do with mass. Mass is the key to determining what's going to happen with those stars. Matter of fact, on the Hertzsprung-Russell, anything that is in this upper right-hand quadrant, these are considered the giants. Things on the main sequence and below, these are dwarfs, and we are in the dwarf pile. If you have a big, bright blue star, these things are like young, hot Hollywood superstars that might be living on the edge. They might live fast and die young. Their lifespan might be 1 billion years or less, and their mass might be 10 times as much. Because they are so big, they're going to just plain burn fuel faster. And that faster fuel burn is going to produce an awful lot of heat, and that heat is what is going to produce that blue color. This is a picture of the asterism, the Pleiades. The Pleiades is an asterism in the constellation Taurus. Taurus the bull is actually chasing these 7 sisters, and these 7 sisters have the Japanese name Subaru. And if you look at the front of a Subaru car, the constellation on the front happens to be the Pleiades. This is a group of young, hot blue stars. So we're now going to start talking about what happens to these fast-burning heavyweights. They're going to start as stars. They're not going to be have as long a life cycle. They will go not just to red giant like our sun will go. They're going to turn into something called a super red giant, then go through a process called supernova. And then there's 2 paths. Either go towards black holes or go towards being neutron stars and pulsars. So let's dive in. When any star starts to run out of hydrogen fuel in its core, the core is going to go through a partial collapse that is going to make it start burning the less efficient fuel like helium. And when that happens, the star is going to get cool and it is going to expand. And when that happens to these big, big, big stars, it's not going to turn into a red giant. It is going to turn into a red supergiant. Now, this only happens to stars that are about 15 times more massive than our sun. If our sun would go supergiant, which it will not, but if it would, its diameter would go out to almost the orbit of Jupiter. Big, big, huge, cool red star. We've been talking about nuclear synthesis and how different elements get produced. Well, super red giants are where we end up with elements up to the element iron. If you remember this diagram I've drawn a handful of times, this is this energy per nucleon diagram. A typical young star is going to fuse hydrogen to produce helium, very efficient fuel source, and as they have to switch fuel and get colder and colder, that's going to fuse to produce carbon and oxygen, and that's sort of where our star is going to end. But in a super red giant, the core is going to have such high temperatures and the pressures are going to be so great that those bits of fuel, carbon and oxygen, are going to start to fuse with other elements, and we're going to reach the pinnacle the top edge of this diagram, and we're going to actually fuse and produce iron. Iron is very important on this chart of energy per nucleon because of the fact that that is about as the maximum that you can get out of normal nuclear fusion. That's about the biggest element you can produce. But all of the iron that is in your car, the iron that is in your blood, most of that was produced in the nuclear furnaces of a super red giant. Back in 1930, there was, I'm going to actually go forward and back again. Back in 1930, there was an Indian scientist, and his name was Subramanian Chandrasekhar. And I apologize if my Indian pronunciation is not up to snuff. Subramanian Chandrasekhar. At the age of 19, Dr. Chandrasekhar discovered something that was very, very interesting, and it is referred to as the Chandrasekhar limit. Now, you have possibly heard his name Chandra, because we Americans are a little lazy, so we abbreviate things. There is an X-ray telescope that NASA launched a handful of years back, and it was named the Chandra telescope in the honor of Dr. Chandrasekhar. Now, what he discovered was something today that we refer to as the Chandrasekhar limit. He found out that stars that have a core mass greater than 1.4 solar masses, almost 1.5 times the mass of our sun, when those super red giants begin to collapse, a weird and crazy thing happens. Now, in a typical star, when a red giant starts to collapse, all it does is change fuel into like helium, changes to carbon, changes to oxygen, and eventually ends up as a white dwarf. But when you have a super red giant, there is so much heat and so much pressure that is produced when this big, big, big star collapses that there is a limit to how fast you can take that much matter and collapse it down. Because it gets such incredible temperatures and pressures inside of that collapsing star, it produces something that is called a supernova. So let's talk about exactly what we mean by a supernova. When we have a core collapse supernova, what occurs is the normal star has got this balance, heat and pressure pushing outward, gravity pushing inward. And when we end up with such a huge amount of matter collapsing inward so quickly, the pressures get so great that you just cannot simply easily switch fuels. So what happens is the star explodes. Whenever you have a supernova, there are always two things that occur, and these two things occur because of Newton's third law. Newton's third law says that for every action, there is an equal and opposite reaction. Well, that equal and opposite reaction means that you are going to have an explosion and an implosion. The collapsing star is going to produce massive amounts of heat and pressure in the core. But that heat and pressure pushing inward is also going to produce an explosion pushing outward. So you get an implosion going in and an explosion going out. The explosions produced by supernova are what make them appear very, very bright. Supernova are relatively rare. We don't see them that often because it's a unique set of circumstance, and we have to be looking in the right part of the sky at the right time to see them. They only last for about a year or so, maybe a couple years, which is very, very fast when you start talking about anything in astronomy. Here's a picture of supernova 2011 FE. Supernovas are always named SN, followed by the year in which they were discovered, and then letters to indicate which one is observed that year. This beautiful collection of pictures lets you see that in the before picture, you really cannot detect a star there. I mean, you really have to kind of use your imagination that there was a star there at all. And in a very short period of days, it went from being not visible to being almost as bright as the center of the entire galaxy. That is brighter than 100 million stars. That's why the supernova, nova meaning new, are such extraordinarily interesting things to see. This is a picture of supernova 1987A, as recorded by the Hubble Space Telescope. And I think it's pretty easy to imagine that right there in that center, you've got that implosion, everything pushing in as that star collapses, and then there is an explosion that goes outward, and that gives you these rings of gas going in all of these different directions. Supernova explosions produce nebula. This is the Butterfly Nebula, and if you look at the Butterfly Nebula, I don't think it takes an awful lot of imagination to imagine that there is an explosion that created it right smack dab in the center. This is the Crab Nebula. Crab Nebula, again, is a leftover supernova explosion that we're viewing. And I always think this is so cool because this is the ultimate recycling. When stars die, they throw a large big stars especially, they throw large quantities of matter out into space, and those large quantities of matter turn into protostars. And protostars end up with proto-solar systems. And you and I, ladies and gentlemen, we are recycled stardust. We have actually been produced, a lot of the atoms within us, from stars that have exploded in the past. Now, supernova explosions are also really interesting because they produce, within a fraction of a second, all of the heavy elements that are beyond iron on the periodic table. Now, if we take a look at the periodic table, everything up to iron can be produced. We start with the light elements here, and we get, I've got to go backwards, and we go heavier and heavier and heavier up to the element iron, and iron is produced on that diagram of energy per nucleon. Iron is right at that pinnacle and gets produced in novas. But in order to get supernovas, and supernovas are the only places where there is enough heat and there is enough pressure to push all of the little positive protons in nuclei together with enough force to make all of the heavy elements on the periodic table. So supernova are essential to you and I and our life cycle and our life story. So what this means is any of the big elements, like the copper that's in the pennies in your wallet, the iron that is in your blood, the gold and the silver atoms in jewelry that you might wear, those actual atoms were made in the fires of supernova just for you. So I think it is quite magnificent that you and I are recycled stardust. Here's a collection of things that I quite love. Here's an old Serbian proverb, and it says, "Be humble, for you are made of earth, and yet be noble, for you are made of stars." Carl Sagan, the great astronomer and host of the old original Cosmos series, his quote was, "The nitrogen in your DNA, the calcium in your teeth, the iron in your blood, the carbon in your apple pies were made of the interiors of collapsing stars, and we are all made of stardust." So I think it is quite magnificent, and it helps connect you and I with the entire cosmos. We know that our sun is a second or third generation star. And we know this because when we look at the spectra of our sun, it contains 67 elements that are heavier than hydrogen and helium. Now, hydrogen and helium were the primordial elements created soon after the Big Bang. So that means that our star has been recycled once. It is the result of one of these explosions and recombinations to make a new star. So is it second or third generation? We're not really sure about that. But you and I wouldn't be here if there was not these explosions. All right, that's going to end this one. And next time we're going to come back and talk about different